Okay, so let's talk kind of the big idea. Simplest way to calculate work is what? Force times distance, right? And any work can also be looked at in terms of change in some type of energy, whether that's springs, whether that's kinetic, whether that's rotational, doesn't make any difference. Any work can be viewed as just some change in energy, okay? Now, you all are used to dealing with KT, which is 1/2 mv squared. Now, you can also have rotational kinetic energy, which is 1/2 I omega squared. So, old school, what does I represent? Moment of inertia, measured in units of kilograms meters squared, right? Because remember, it's all some form of mass times radius squared, right? What's the only time you can use MR squared? Two situations. Point mass and thin hoop, okay? It's the only time you can use the only time you can use MR squared. Point mass, thin hoop. Otherwise, you have to look up the equation. So, what's omega measured in? Radians per second. But that's going to get squared. So I get kilograms meters squared over second squared, which oddly enough, if you look at translational, that's kilograms meters squared over second squared. So we end up with the same units. So I take this bicycle wheel. Did I just do work? Yes. Why? Force over distance. And what did I change? I changed the rotational kinetic energy of the wheel. So what was the initial rotational kinetic energy of the wheel? Zero. So if I know what my final rotational kinetic energy is, I know how much work I've done. Okay? Because work just equals some change of energy. Cool. Now, force times time equals what? Change in momentum. Now, you all are used to, up to this point in time, that's being mass times change in velocity. Okay? Up to this point in time, the change has always been associated with velocity. However, if you look at how rocket engines work, okay, and how they create force, we change literally the change value. So with rockets, it's still force times time. That still equals change in momentum, but that's going to be change in mass times the velocity. So if you divide both sides by time, so if you want a big force from a rocket engine, you want a big change in mass per unit of time. This V, listen to me, didn't mean for that rhyme, is not the velocity of the rocket. This is the velocity of the escaping gas. So if you want to create a lot of force from a rocket engine, you consume a lot of fuel per unit of time, and the gases are ejected at a very high velocity. So in a cool way to look at this,
20 seconds.
So this is a solid rocket booster that they're getting ready to
T-minus
test.
15 seconds.
Problem is you can't shut them off when they
T-minus
start.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, fire. T plus 5 seconds.
That's a lot of fuel being consumed, okay?
T plus
So
10 seconds.
what's happening is that if you were to calculate the force,
Is it 3 minutes long of it just going?
yeah, it gets boring after a while. No, 2 minutes, they let it boost. It gets pretty boring. So if you want to create a big force from a rocket engine, you consume a lot of fuel per unit of time. But what's the downside of that?
You won't have as much time.
Well, then that's going to carry a lot of fuel. A lot of fuel is heavy. And so then you get a bigger opposing force, then you get more inertia, and then you get a smaller net force. But the beauty of it is that as that rocket goes through the fuel, what happens to the opposing force? It decreases because you have less mass and you have less of an opposing force. Okay, so a lot of these are going to be old school, okay? Like when you get to number 3, you have a dart compressed against a spring. You have a spring constant. We're going to push that against it, we're going to let go of it, and we're going to launch the dart, okay? Potential energy is going to change into kinetic energy. When you get to number 4, okay, you have a solid cylinder. Moment of inertia of a solid cylinder is 1/2 mr squared. Okay, do not use mr squared at number 12. Remember, torque equals 2 things. What are the 2 things that torque equals? Force times radius and I fish. Keep that in mind. Okay? When you get to number 5, okay, on number 5, I tell you it's a perfectly elastic collision, okay? That's when you're going to use those equations, and I've got the equations down below, okay? To calculate the new velocity of the bullet, the new velocity of the target. So those are down below. So you've got questions from the book. When you get to question number 10, where you have the Earth and Moon, here's the Earth, here's the Moon. To give you some perspective on how far away the Moon is, you could stack every planet in between the Earth and the Moon. Saturn, Jupiter, Venus, all the planets, okay? I draw it like it's fairly close. It's not. If that was to scale, where's my Earth? There's the Earth. If the Moon was the size of a tennis ball, the tennis ball would be in the back corner of the room. Okay, to scale, that's how far away the Moon is, okay? We always draw it like it's close. It's not. It's a long way away, okay? So what I would recommend on number 10 is that you let the position of the Moon or of the Earth have a value of 0, okay? Make that the point where you judge all the positions from. Then you've got some problems from the book, and then you've got some multiple choice questions. Some of these, I know you're going to have questions on tomorrow, so especially on some of those multiple choice questions, if you read those, go, oh my God, I have no idea how to do them. Don't flip out. We'll talk about them tomorrow. Okay? All right.